In the previous video we looked at the idea that a current can produce a magnetic field, and so that means that if the current produces its own magnetic field and is then positioned in another magnetic field, we're going to see some forces of attraction and repulsion that will occur that means that it's going to experience a force. So first note here is that we have that idea of a magnetic field being produced by a current, and as I said, the second key thing then is if that conductor is placed in a magnetic field, that means that it's going to experience a magnetic force due to the interaction of those two magnetic fields. And the easiest way to deal with this is to have a look at a diagram showing the fields and how they would interact, and identify what the magnetic force is, or where that magnetic force is going to come from. So we'll start off looking at a magnet, or the south pole of a large magnet, and then we'll have a north pole of another magnet down the bottom here. So what we're really doing in this region is just establishing a fairly strong and relatively uniform field. So south pole at the top, north pole at the bottom, and that means it will have magnetic field lines that will be oriented this way. Note that we could draw lots of field lines here. I don't want to clutter it up too much, so I'm only going to draw a few. So that represents a magnetic field. In that magnetic field we're going to have a conductor, and the direction of that conductor is going to be towards the front, so it's sort of coming out. We'll have a current flowing through that conductor that's coming this way. So I'm going to change the colour of the field lines here just so we can see them a little bit more clearly. So we know that the field lines are going to be concentric circles, and so they'll be directed in this sort of fashion. So I'll just draw again one set of field lines around the conductor in that region, and we know that they'll be in an anti-clockwise direction here. So that's the magnetic field produced by the conductor itself. Now, to make sense of the direction of the force that's going to act here, we need to consider this region here and this one on this side as well. So to explain those regions in a bit more detail, we're looking for regions where parallel field lines are interacting, and in those two regions there you can see that on the right hand side they are in the same direction. So this region here, just to make it clear, so we can see that the red field lines are directed up, and likewise in that region the green field lines are directed up. When we have that situation occurring, that leads to a repulsive force. On the other side, where field lines are in opposite directions, we'll see that it is an attraction. So in this case, we're looking at this region, and if we combine those two, we end up with a resultant force that in this case is going to be to the left. And that's because of the arrangement of the current and the magnetic field. So we can identify then that the force acting on this conductor is in that direction. Now, to identify the direction of the force, we're going to use another rule here, and that's the right hand palm rule. So when we're talking force, we've got three quantities to consider. So the direction of the force is given by the right hand palm rule. And to go through what that means in a bit of detail. So the three things that we need to be aware of: the first is the thumb, and that represents the direction of conventional current. And again, if you think of it as being that you only have one thumb and there's only one current, that can help to remember which is which. The second is fingers, and they represent the direction of the magnetic field. That's the external magnetic field in which the conductor is placed. So the direction of the field lines. And note that in this case the field lines are straight, so you don't curl your fingers around at all. And finally is your palm, and that represents the direction of force. And the way to remember that is that you use your palm to push on something or to apply a force to something. So you can use those three to help you make sense of the direction of the force itself. Now to add another diagram here. So here's a hand representing this scenario. So you can see the thumbs pointing out towards the left in the direction of the current. Fingers are pointing up in the direction of the magnetic field. And palm is pointing to the left in the direction of the force. So you can see all three of those are perpendicular, and so we have the force being produced by the current positioned in a magnetic field. There's another key aspect to be aware of here, and that's the orientation of the current in the magnetic field. By identifying that the force will be at its greatest when we have everything being perpendicular. And that means the current is perpendicular to the field lines. So to make sense of that, again with another diagram. So if we once again orient the magnetic field so that it is directed vertically upwards, the current being perpendicular to that is going to be directed towards the left. So we'd have this line representing the current going this way. That situation where we have 90 degrees between the current and the magnetic field will produce the maximum. Now if the current is not perpendicular, we need to resolve it into components, and we'll then consider the component that is in that perpendicular direction. So even though current is not a vector quantity, we can use the length that is in the magnetic field in order to calculate the perpendicular component. So if we look at that diagram on the left, what we can do is identify that there is a length of this conductor, L, that is in the magnetic field. And so if we then have a conductor that's not perpendicular, so again if I just redraw these field lines, and in this case we'll have the conductor at an angle. Imagine it's in this sort of direction now. The length that we're dealing with is now in this direction here, and we need to find a perpendicular component. So what we're going to do is break this up into a component that's across the way here, and then a component that's up this way. So you can see that we have a right angle triangle there, and the side that we're interested in, being this one along here, is going to be given by L sine theta, where theta is the angle between the conductor and the magnetic field. So essentially all we're considering there is a component that's still perpendicular, so the parallel component doesn't actually produce any force, and the angle in that case for theta would be 0. So the magnitude of the force then we can calculate by knowing all of those quantities. And the equation is as follows. So the force F is going to be equal to the magnetic field strength multiplied by the current multiplied by that perpendicular component of the conductor that's in the magnetic field. So that's the equation that you need to be familiar with. It's in the data booklet. And the quantities here are that F is the force in newtons, B is the magnetic field strength, and that will be measured in Teslas. I is the current in amps. L is the length of the conductor in the field. And the length, as always, is measured in meters. And theta is the angle between the conductor and the field. So when the conductor is in the same direction as the field, that will be an angle of 0, and when it's perpendicular, that's where the angle will be 90 degrees, and so we'll have maximum force when it's perpendicular. So when a conductor is placed in a magnetic field, it will experience a force that's given by that equation, with the direction determined using the right-hand palm rule. In the next video, we're going to have a look at what happens when it's a single charge that's moving through a magnetic field.